say point. Okay, so what's the voltage of the capacitor and the resistor after 1 second, and the charge stored in the capacitor and the current in the circuit after 1 second? So we can answer that and say how many seconds does it take for the voltage of the capacitor to equal twice the voltage of the resistor? So these are several different questions we can ask, although we could ask many more, but I'm just giving some random possibilities here. So what is the voltage of the capacitor and resistance after 1 second? Here I'm giving you the time, and then I'm saying solve for all the unknowns. Here I'm saying I'm giving you a certain condition. How many seconds will it take for this condition to be satisfied? Here I'm also giving you a condition, you see? So how many seconds does it take for PC to reach its peak? So let's do the first one. After 1 second, we can solve for the QC and the I. QC was CVB 1 minus e to the minus t over RC, right? And then we're going to have here QC. C is 0.2 millifarads. This is 20 volts. And then RC, I've done it so it's pretty easy. It's just this times this, and the milli and the kilo cancel. So it's just 1.6. So then that's going to equal, this is going to be 4, right? 4 millifarads. I mean, 4 millicoulombs. 4 millicoulombs. Okay, so then we can just put here 1 second into here and then solve for the QC. Okay, so the charge is going to be 1.85895 millicoulombs at 1 second. And then the voltage of the capacitor is going to be the charge divided by the capacitance, right? So Q over C. What was my C? 0.2. So this guy divided by 0.2, 9.29. 9.295 volts. Well, since this one, the capacitance is millifarads, the millis will cancel, and it's just be straight up 9 volts. Okay. Now, I guess I could kind of cheat and say, oh, okay, I know that these two are in series, so whatever voltage this guy has, this guy is going to have the opposite voltage, right? They have to add up to 20. All right, let's just do it that way. So 20 minus 9.295. So then the voltage of the resistor is going to be 10.705. So one of them is going down, one of them is going up, right? The voltage of the capacitor is going up. So then once you know the voltage of the resistor, then you could figure out the current, right? Voltage of the resistor divided by R. So divide this by 8. 8 kilo ohms. So divide this by 8. So 1.338 milliamps. That pen is kind of dead. 1.338 milliamps. Okay, that's it. So that was pretty easy, not too bad. Second question, how many seconds does it take voltage of the capacitor? So in other words, I want this guy to keep building up all the way, and then this one dying, voltage of the resistor. So until this is twice that. Okay. So this one, I could also do it this way. Since I know that the two voltages have to add up to 20, voltage of capacitor, resistor plus voltage of capacitor is 20. I could say if I want the voltage of the resistor, so since I already have an equation for the voltage of the capacitor, right? So I could say I want voltage of the resistor to be half as much as the voltage of the capacitor. So then I want the voltage of the capacitor to be what? 3 over 2, so then it's going to be 40 over 3. So I want the voltage of the capacitor to be 40 over 3, such that the resistor will be 20 over 3. And then together, when you add them, you're going to get 20 volts, right? So then I already have the equation for the voltage of the capacitor. Voltage of the capacitor. It's just simply this equation without the 0.2 millifarads, right? It's just this thing. Yeah, so it's just 20, 1 minus e to the minus t over 1.6, right? And that should, we want it to equal 40 over 3. So then we can solve for t right here, right? What is that going to be here? This is 2. And cross multiply the 3. All right, and yeah, So then 3 minus 2 is going to be what? 1 is 3 e to the minus t over 1.6. Right, so this one went to the other side, and then I subtract 2 from this, and you get this, and then you divide by 3. Then you take the ln of both sides, and the ln of this will just be negative t over 1.6. And then this would be negative ln of 3, so the negatives will cancel. So it's just going to be, t is just going to be 1.6 times ln of 3. Uh, 1.75. See, the time constant of this circuit was what? 1.6 seconds. So everything is happening kind of fast. At 1.6 seconds, the capacitor is already charged to 63% of its value. And then the resistor has already discharged to 37%. Yeah, so that kind of makes sense. By 1.75, you're already past the time constant, 1.6. So the capacitor has charged even more. So it makes sense that by that point, the capacitor is twice the voltage of the resistor. Okay, next question. How many seconds does it take for the energy of the resistor to be twice the energy of the capacitor? Is that scenario likely? Let's see, remember how the equation looked? The energy of the resistor kind of rose quicker, and then this one was like this, but then they eventually reached each other. And then the energy of the battery was like that. Yeah, so you could have most of the energy lost in the resistor, such that you could be, this is the resistor and this is the capacitor. So you could be the energy of the resistor twice the energy of the capacitor. But the capacitor cannot be more energy than the resistor. It's always lower. So if it was the other way around, you would say there's no answer, right? If that was a test question, how many seconds does it take the capacitor's energy to be twice? No answer, okay? So then how do we solve that? We want the energy of the resistor to be twice the energy of the capacitor. Okay, what was the equation for the energy of the resistor? Oh, okay, it was this one. Right, and then the energy of the capacitor was this is energy. Energy of the resistor, we want it to be twice the energy of the capacitor, so we put an extra 2 here. So this is the equation for the energy of the capacitor, energy of resistor. How do we proceed now? Oh, I can cancel this, then factor out this, and 1 minus e to the minus will cancel one of this. So if I factor one of them, you get e to the minus t over RC is equal to, and then one of these will cancel one of these. So we'll just get 2 1 minus e to the minus t over RC. Yep. So then this one distributes and then goes over there. So you will have 3 e to the minus t over, and then what was my RC in this case? 1.6. So 3, 1.6 is equal to 2. And then you're going to have 2/3 ln of 2/3, right? So you're going to have t is equal to 1.6 ln of 3/2. Because 2/3 ln of 2/3, then you're going to flip that. You're going to have ln of 3/2 and then 1.6. Okay, so this negative will flip those 2/3. Okay, so let's see here. We get. It should happen relatively quickly. That's when the resistor dominates. So you're going to have ln of 1.5, okay, times 1.6. Oh yeah, very quickly. 0.64. T is equal to 0.649 seconds. Okay. And what was the last question? How many seconds does it take for the PC to reach its peak? So PC doesn't stand for politically correct. It stands for the power produced in the capacitor, right? The rate at which you're storing energy in the capacitor. Right? You see things very differently when you're learning. Everything has different meaning. So basically, I'm asking this question here graphically. I want to know how long it takes for the power in the capacitor to reach its max this time. In this case, it was 6.931 seconds. Right? So how do we solve that? We want to basically maximize this function. Right? So then just take the power function, right? The power equation for the capacitor, and then take its derivative and set it equal to 0. Take the derivative of this function. So what was my power equation? I've got so many equations here. Power equation for the capacitor. Power equation for capacitor. You know what? Let's just go to the formula sheet. It's just going to be this equation minus this equation, right? So VB squared over R, and then, okay, so then that's pretty easy. So it's just VB squared over R, e to the minus T over RC minus e to the minus 2T over RC, right? So in our case, it's just 10 squared over, what was my R? 2 kilo ohms. E to the minus T over 1.6 minus e to the minus 2T over 1.6. Okay, now take the derivative of this and set it equal to 0. Okay, so then this is going to be 100 over 2. That's going to be 50 milliwatts. And then the derivative of this is going to be negative 1 over 1.6. And the derivative of this is going to be negative 2 over 1.6. So plus 2 over 1.6 e to the minus 2t over 1.6. Set this equal to 0 to solve for the time.
Professor, a question?
Yeah.
Did you mean to say dp c over dt?
Oh, yeah. I meant dp dt. Yeah, the derivative. Yeah. Okay, then you're going to have, let's see, we could factor out the e to the minus t over 1.6, right? So 15 milliwatts, e to the minus t over 1.6. Oh, we could factor out the 1.6 also, right? So 1.6. So then we're just left with negative 1, which is this, plus 2 e to the minus t over 1.6. Because I'm factoring out the t, so then we're just left with one of them. Right? Okay, I think we're good. Then set this equal to 0. So then 2 e to the minus t over 1.6 equals 1. Okay, so then you have e to the negative t over 1.6 equals 1/2. And then t is equal to 1.6 ln of 2. So all our answers are something like the time constant, right, times ln of something, ln of 3 or ln of 4, depending on what the condition is. 2 ln times 1.6. Oh, so that's the time that maximized, that the power of the rate at which the capacitor is being charged reaches its max. You see, 1.109 seconds. So it's a little bit less than the time constant. The time constant is 1.6 seconds. So before reaching the time constant, you've already maximized on the capacitor, and now it's going down. From there, you can answer the other questions, whatever other questions that the problem asks. Okay, good.